So I'll start off with an introduction to what submarine canyons are and why they are important to study. Then I'll talk about the model that I used. Then talk about scaling and the results, and finish off with some conclusions. So this figure down here was taken from a paper written by Alan and Hickey, and I just thought that it was a really good one to represent and to visualize what a submarine canyon looks like. So submarine canyons are found just off the coast, and this is the continental shelf here. And so this is, I'll talk about the slope. This is the slope here. This is the shelf break. And at the shelf break, this, the topography, the slope just becomes much more steep. And so there's a couple flows during an upwelling event. The surface flow goes across over the canyon. Then there's an upwelling current, and then deep flow that circulates in the canyon. So these canyons are regions of enhanced upwelling. So this is important for bringing nutrient-rich water from depth up onto the shelf. And this is really important for productivity, and these regions can be very biologically active. And so difficulties in the field and with numerical models, this just means that a scaling analysis is really useful in estimating the strength of canyon upwelling. And so in the same paper by Allen and Hickey, they proposed a scaling for a number of quantities. And so this scaling did not allow for any variation in the shelf slope. But when I first started on this project, looking into the scaling a little bit more, we found that the continental shelf slope does play a big role in canyon upwelling, so it should be included in the scaling. And so this was something new. No one's ever looked at the continental shelf slope in terms of canyon upwelling before. So to test the scaling, I want to have a number of canyon simulations. So to do that, I used a numerical model, the Massachusetts Institute of Technology General Circulation Model, or MIT-GCM, and I used Compute Canada's Western, so a really fast computer to run the model. So then over there, I have my model. So that's the topography of a laboratory tank. And so the tank's about 1 meter in diameter and about 9 centimeters deep. Here's the continental shelf, a flat abyss, and then here's the canyon cut into the shelf there. And so I varied numerous things. I varied the strength of the flow velocity, U, so that's coming into the canyon. And later I'll talk about V velocities, and those are velocities in the radial component. I also varied the stratification of the water, represented by the buoyancy frequency N, the Coriolis parameter F, so that has to do with the rotation rate of the tank, the shelf slope S, as well as the canyon geometry. So this is just a close-up of the canyon, and on here I've plotted in white the 2 centimeter shelf break contour. And so different length scales that I use in the scaling include the length of the canyon L from the shelf break to the head of the canyon, the width W measured at half length, and that's just between the 2 points where the topography starts to dip into the canyon. The width at the shelf break measured by these two corners, and another width scale RW, again at half length, but this time just in between the 2 centimeter contour. And if we draw a circle that fits in this contour, the radius of that is the radius of curvature of the canyon. And so just to give some more motivation why we need to include the shelf slope, I've plotted on here the scaled values that Allen and Hickey had in their paper on the x-axis for the depth of upwelling flux and deep water stretching, and then the observations or the results from the model on the y-axis in each of these cases. And then I fit some coefficients so I could draw a one-to-one line on these plots. And ideally, we would want all these cases to fall along those one-to-one lines. But we can see that there's lots of scatter, and we have really high normal residuals. And in particular, for this, the flux cases, these red ones are know, high U velocities and the different shapes or different slopes. So you can see there's tons of scatter there. And so why is this shelf slope important? Well, here I've taken a couple cross sections from a double slope canyon. So this, there's a really steep continental slope here. And so the dashed line is the topography away from the canyon. And then the solid line is the topography through the center of the canyon. And so we spin the tank for 30 seconds, and then we have upwelling, and we kind of stop there because this is, once it reaches kind of a steady state. And so here we have the flow coming out of this stream, and so these are the isopycnals, and the thickness of the isopycnals, the tilted isopycnals above the head depth, that's ZB, and the depth of upwelling Z is the depth from which the deepest water makes it to the head depth of the canyon. So if we have dense water moving upward onto the shelf, there'll be a back pressure acting downwards, and that'll restrict further water from moving upslope and reduce the amount of upwelling that we have. And also, we'll have gravitational force acting downslope, which is balanced by the Coriolis force acting upslope. And so the velocity, or the dense blob will want to translate back upstream. So that's in the opposite direction, and that will further reduce upwelling. And so taking these into consideration, as well as redefining the velocity of the upwelling stream, we can come up with new scales for the depth of upwelling. So dH is a depth scale, RL is a Rossby number, F is a function of Rossby numbers, which is used just to relate the U and V velocities as flow crosses the canyon, and A1, E2, and E3 are coefficients that we fit. And so this term right here, this is our contribution to the scaling. This is the effect that the slope has on the depth of upwelling. And then here we have the flux and stretching scales. So stretching is the vorticity divided by the Coriolis parameter. And we have the same kind of terms here and here, and that's the effect of the slope. And the B's and D's are coefficients that we fit. And so now that we have scales, we want to look a little bit more into the model results and our observations. So here I've plotted upwelled water. So that's water that was below the 2 centimeter shelf break and is now above. And so this is the thickness of the water above the shelf slope for a double slope case, basic case, and flat slope case with a high incoming velocity. So we can see that the double slope has much less upwelling than cases where we have flat slopes that are higher velocities. And so we want to measure the flux. So if we take the volume in each grid cell over theta, so we plot volume versus theta, we get these green curves. And there's a number of different types of upwelling. There's the friction along the side here, so we can ignore that. There's time-dependent upwelling, which is symmetric in the canyon, but the scaling is only good for advection-driven upwelling. So that's all this water that we see to the side here. And in some cases, like that flat slope high U case, there's also an additional source of upwelling here, and that's just due to internal waves. And so isolating all these different types of upwelling, and so we can see those in the green lines. We fit some Gaussian curves, and then we can isolate just the volume upwell due to advection. So we do this at 30 seconds and at 25 seconds and take the difference, and we can find a flux that way. And then for the vorticity, so the vorticity is just the curl of the velocity, and in particular we're just interested in the vertical component of that. So this is the expression for the vertical component of vorticity in cylindrical coordinates. So I plotted that on the right side here. However, there's lots of shear in the azimuthal velocity. So we just want to look at the vorticity generated by the canyon. So we just take that first term here, and so by plotting that, we can see this red blob here, that's the cyclonic vorticity in the canyon. So we take the maximum value, and we use that as our observations. So here, making the same plots that I showed earlier, with the new scale values on the x-axis, and the depth of, and the observations from the model on the y-axis, and the one-to-one line, we can see that all these points fall really closely to this one-to-one line, and we have a lower norm of residuals. So we were really pleased to find that this worked, and to find this plot. We did the same thing for the upwelling flux with the new scale values and the observations. And there's a little bit more scattered here. However, it's still an improvement from before. And same thing for the deep water stretching. It's still, a little bit scattered, but it's definitely better. So in conclusion, the continental shelf slope plays a role in canyon upwelling, where flatter continental shelf slopes have larger depths of upwelling fluxes and deep water vorticity. And so for future use, we can look into how the scale works for real world canyons, and the expectation is that it should work. Thank you.
So you had that Rossby number function there, right?
Yeah. The F, yeah.
Can you just describe a little bit how you chose that? Is that for asymptotic reasons? Is that dimensional analysis?
Yeah, so here, normally flow will want to follow the isobath, but when we have upwelling, it will cross. And so for higher Rossby numbers, the flow will tend to cross the canyon. And so my supervisor came up with this number. And so for high Rossby numbers, so C1 and C2, those are about order 1. So F is about 1. And so sorry, I got a little bit confused there. But it's, yeah.
So at low Rossby numbers, we'll put high Rossby numbers.
Right.
Okay.
Yes.